Bonjour, bienvenidos, bienvenue, welcome to video key for Coulomb's law worksheet number 2. Hooray! So, real quick, just to do some background on Coulomb's law. Coulomb's law is basically an equation that describes the relationship between the force of two charged objects. So, like, from what we've learned so far, if we have two positive charges that are close together, they will experience a force. They will interact with each other. Specifically, two positive charges will what we call repel or push each other away. So these two charges will experience electric forces that push each other away. Similarly, two negative charges will push each other away. They will also repel. And a positive and negative charge, opposite charges like this, they will attract. They will pull each other together. So these are what we call electric forces, and Coulomb's law talks about how big these electric forces will be. So consider like two examples, right? In example one, I have two small charged particles, very, very small amounts of charge. Now, will these two charges push each other apart? Yes, they will. Will they push each other apart strongly or weakly? Well, because they're very small charges, not very charged objects, then they won't repel each other very strongly. The more charged an object is, the stronger its interaction would be. If you think about, say, rubbing a balloon on your hair, if you rub it just a little bit, it only becomes a little bit charged, and then it only attracts to your hair a little bit. Less charge, less force. If you really rub it on your hair, it becomes very charged, and that means that it'll have a very large interaction, right? More charge, more force. So two small charges will repel each other a small amount. Two large charges will repel each other a large amount. So what this implies is that the amount of charge how much charge you have is directly proportional to force. In other words, if charge gets bigger, force should also get bigger. If the amount of charge gets smaller, the amount of force should also get smaller. We call this Q. Q is the amount of charge. And because to have an interaction, you need two charged objects to interact, we usually have two charges, so we call them Q1 and Q2. Sometimes these are also referred to as like a lowercase q and a capital Q, but we will use Q1 and Q2. So that's one example of something that affects electrical force. We would write this as force is proportional to Q. Now, in example number 2, consider two charged particles that are very close together. They're really close, so they push each other away really hard. A large electrical force. If I take those same two charges and I separate them a great deal, the amount of force between them goes down. In other words, more distance means less force. Less distance means more force. And what this implies is that force is inversely related to distance. In other words, force is proportional to the inverse of distance, what we call r. But when researchers experimented with this, they actually found that this is not quite true. That it's not just inversely related to r. If it actually is inversely related to r squared, it's called an inverse square relationship. If you double distance, what they found was that the force doesn't go down by a factor of 2. It goes down by a factor of 4, 1/4 the force. So 2 times the distance means 1/4 the force. 3 times the distance actually turns out to mean 1/9 the force. In other words, it's not just the inverse. The inverse would be, say, 1/2 or 1/3. It's the inverse squared, 1/2 squared or 1/3 squared. So when you put these two things together, we say F is proportional to Q and F is proportional to R, 1/r squared. That leads us to Coulomb's law, that the electric force is going to be directly dependent on Q1 and Q2 and inversely dependent on the distance squared. And the last thing that we have here is this constant K, where K is just a number. It's just an experimental value that says you have to also multiply by this much every time. And this is called Coulomb's constant. So that's a really brief overview of what Coulomb's law is. And for our purposes, we're more or less just going to be plugging numbers into this equation or qualitatively looking at, if I do this, then what would the result be? So going back to my worksheet here, you can see Coulomb's law right here, where I have K times Q1 times Q2 all over the distance squared. And K is given as this number. So the first question asks, what's the force between charges of 10 microcoulombs and negative 50 microcoulombs located 20 centimeters apart? For this question, we're going to have to do some unit conversion, which I don't expect you to have memorized, but it's really easy to look up. So this little symbol right here means micro, if you just Googled it. And that means times 10 to the negative 6. So this number is actually 10 times 10 to the negative 6 coulombs. And this number is negative 50 times 10 to the negative 6 coulombs. It's a very small number. Centimeters converted to meters would be 20 centimeters times 10 to the negative 2 meters. Centi means times 10 to the negative 2. So I know Q1 equals 10 times 10 to the negative 6 coulombs. Q2 is negative 50 times 10 to the negative 6 coulombs. And the distance D is 20 times 10 to the negative 2 meters. Plugging all this into my equation, I get that the electric force is going to be equal to 9 times 10 to the 9 times 10 times 10 to the negative 6 times negative 50 times 10 to the negative 6 divided by 20 times 10 to the negative 2. And at this point, you can just start plugging things into your calculator to find an answer. So I'm going to do that right now. I'm going to have 9 times 10 to the 9th times 10 times 10 to the negative 6 times negative 50 times 10 to the negative 6 divided by 20 times 10 to the negative 2 squared. And that's going to give me a value of negative 11.25 times That's just it. 11.25. And that's newtons. So that would be my final answer. Next up, we have two spheres of identical charges. So what that means is that Q1 equals Q2. And they are 75 centimeters apart. So the distance is going to be 75, or let's just call it 0.75 meters. The force between them is 0.3 newtons. What is Q? So I'm going to go ahead and write out my equation. The electric force is K Q1 Q2 over d squared. Now in this case, because Q1 and Q2 are the same, I can actually just write that as Q. So I get K times Q over d squared, or the electric force is equal to KQ squared over d squared. Now I have all of the information I need to plug in and solve. So I'd have 0.3 equals 9 times 10 to the ninth times q squared over 0.75 squared. Again, at this point, you can plug it into your calculator. I'm going to do some quick simplification and say 0.3 times 0.75 squared equals, divided by 9 times 10 to the ninth equals q squared. And then solving for q, get 0.3 times 0.75 squared divided by 9 times 10 to the ninth equals, and then we're going to square root that. So I get Q equals 4.3 times 10 to the negative 6 coulombs. And in this case, what I can tell is that these two objects are repulsive because they're the same charge, right? Which means that they're either both positive or they're both negative. And so they're going to be pushing each other apart. All right. So now let's look at number 3. And number 3 doesn't have any real numbers. It's just qualitatively looking at the relationship. Remember what we said here is that force is proportional to charge, and force is proportional to the inverse of the distance squared. So, A, if the charge of one of the particles is doubled, what happens to the force? Well, force and charge are directly related. So whatever happens to charge, the same thing happens to force. So doubling one of the charges would double the force. Part B, if instead both particles are doubled, well, that doubles the force for each one, right? So you double particle 1, force doubles. You double particle 2, force doubles a second time. So that's 2 doubles, which is quadrupling. In part C, we say the distance is doubled. The force becomes what? Well, if distance is doubled and force and distance have an inverse squared relationship, then it's the inverse squared. So I'm doubling R, squaring that, and then dividing by it. So that's 2 squared dividing by 2 squared. In other words, I'll have 1 over 2 squared, which is 1/4. And lastly, if the distance is halved and the charges of both particles are doubled, what would happen? Well, I already know that in B, doubling the charge would quadruple the force. In part C, I said halving the distance. Oh, sorry, different question, my bad. In this case, halving the distance, 1/2 r, would lead to the force going up by a factor of 4 times the force. And 2q1 would lead to doubling the force, and doubling q2 would also lead to doubling the force. So in this case, I would have a doubling from one charge, another doubling from the other charge, and a quadrupling for the distance. That would be 2 times 2 times 4, which is 16 times as great. And then lastly, we're given Q1 equals Q2, and that is 2.5 times 10 to the negative 6 coulombs. The force is given as 0.5 newtons. What is the distance between them? So F equals K Q1 Q2 over D squared. 0.5 equals 9 times 10 to the ninth times Q, 2.5 times 10 to the negative 6, times Q again, 2.5 times 10 to the negative 6, divided by D squared. And in this case, we want to solve for D squared, or solve for D. Simplifying this, I would have D squared equals 9 times 10 to the ninth times 2.5 times 10 to the negative 6th times 2.5 times 10 to the negative 6 again, all divided by 0.5. And at this point, you can plug it into your calculator and solve. And what I get is, let's see, 9 times 10 to the ninth times 2.5 times 10 to the negative 6th divided by 0.5, and I get a distance of 0.34 meters. Final answer, and we all done. So that's Coulomb's law. For the most part, it's just going to be plug and chug, and then some of those straightforward questions on if I change this about it in the equation, what would the result be? And that's all. Enjoy.